Okay, we are live. All right. Today we're gonna switch gears a bit. First of all, hello. It is currently 3:35 p.m. I was supposed to live stream this morning, but I decided to not stream what I wanted or what I was doing. But I already skipped a few days, which is pretty bad. One second. Yeah, did I skip? Okay, I skipped the past 2 days. Yeah, I think today what I wanted to do is look at PyTorch and see how we can optimize for performance. I think this is a very interesting topic, and given my past experiences, I think this could be very fun. So what I'm gonna do is I'm gonna spend some time reading this and seeing if I actually already know this stuff, and then I'm gonna pull out my notes and I'm gonna see if there's anything. First of all, let's talk about what I know, right? What I know is, okay, let's say we are training a model and we want to optimize its performance. That is, we want to reduce the time it takes to train a particular model, and we're not talking about like, okay, we want to make our model more accurate or make our model make our model more accurate, or play around with like data augmentation. We're not talking about that. We're just talking about, okay, we have the fixed model and we want to accelerate its training, so better leverage the GPU. And this is performance tuning. Go accelerate. And if you can accelerate training and performance, you can save a lot of money, and you can reduce the amount of time that it takes to train these models. So it is important to understand this. So we're gonna go explore what does it take. How can we actually eliminate the time, right? So there are different bottlenecks, right? The main bottleneck that I know about, for example, is the overhead of copying between your CPU and your CPU memory and your GPU memory, if you're not talking about like a unified memory system, right? So if you have your data is stored in your disk, right? Let's say we're training on images. There's some overhead between loading your images on disk onto your CPU RAM, right? And then the computation is done in your GPU, so then there's another copy into your GPU. So your data loader, right? One is like loads it. Ideally, you don't even go through RAM. You just load it directly into memory. And then there's like compute bound and memory bound. Something else bound. Usually we're bounded by these two things. But I was like talking to chat yesterday, and it was saying like something else. Let me try to pull it up and see what it was talking about. Compute bound, memory bound, and data bound. Okay, I guess data bound this is your data loader. Okay, memory bound can be like GPU memory bound, because GPU. Okay, let me just take whatever chat is saying here. So I think like when we're trying to make programs more performant, first we need to identify the bottleneck, right? Because let's say our program is compute bound, so that means like computation, it takes the most amount of time, and you're accelerating, your memory, like you're improving the rate at which you can feed data, or the rate at which you can, like you're making memory transfers faster. That will not have a big impact because your program is compute bound by the end of the day. And so that's why it's important to first identify the bottleneck. And once we identify the bottleneck, then we need to figure out how to eliminate that bottleneck, right? And so this is the part that I'm less familiar with. I think you can have a good idea of like, actually I think I'm just a total noob right now. Like, during my times I've learned some of this, but I haven't done too much of this actual work. So let's go and read this. Changing a few lines of code. Yeah, so first of all, what is pin memory? This is good, actually. PyTorch. Okay, we know this. I'm glad I know all of this. Okay, so pin memory ensures that the memory exists on your physical, in your actual physical RAM, as opposed to secondary memory, because modern computers use virtual memory, and we load data in pages, but parts of the pages some pages can exist in RAM, some pages can exist in secondary memory. If it exists in secondary memory and you try to access it, you get a page fault, and then you need to load it in to your main memory, right? And this can have a lot of overhead, because now you're reading from secondary memory, loading it into main memory. But the reason we came up with virtual memory is because we had very limited memory at the time, and also we can sort of abstract away physical memory from logical memory, right? And so now each program can just use virtual memory and have the illusion that we always have access to memory address 0, even though physically on the hardware, there's only at most one program that can use physical address 0. Okay, so typically when a program access a page fault occurs, and so when you pin memory, we force the content to stay on in main memory. There's so many good articles, huh? Oh, visualize ingredients. I don't know what page locked means. So pin memory is equal to page lock. So we don't allow the computer to swap it out onto disk because your RAM is full. I mean, it must ensure that first it exists onto main memory, right? So there's synchronization after each CUDA copy async. When you copy from CPU to GPU, what is the thing is responsible for this copy? Like when we read to RAM, we have the AMMU that does all this stuff, right? I think so, right? So like doing all the RAM stuff, loading from secondary memory into main memory uses a MMU. It's a DMA engine. the storage controller. And it's interrupt driven, right? Except when, okay. So this sentence I don't understand. So when I'm copying from CPU onto GPU, what happens is usually it's the driver. There's some DMA, like there's some DMA engine, like direct memory access. Yeah, this is wrong, huh? There's coherency. Yeah, so as I was saying, when we copy data from CPU to, or like when we copy data from disks onto our RAM, usually what happens is we issued a read, right, from our disk, and then there's some driver for the for our disk, and it has its sort of own DMA engine. So we initiate a transfer, but while the transfer is being conducted by our DMA engine, the CPU can do other things, right? And then it's going to trigger an interrupt when the data is done. But while the data is being copied, I suppose that region of the memory is reserved, and you can't do any, you're not supposed to use it. It's reserved for the DMA engine to copy. So similarly, when we copy from CPU to GPU, the same thing happens. Okay, let me explain to chat and then let it validate for me. I just want to make sure my explanation of how things work is correct. So basically, when we're reading from disk, right, when we do a read operation, that's a system call. And what happens is that our CPU will communicate with the driver and tell it to initiate the transfer of data from disk onto a particular region of memory. And while that transfer is being done, it's a DMA usually engine that does this transfer so that the CPU can do other things. And so it's doing that transfer. And when the transfer is done, it triggers an interrupt. So during the transfer, the CPU is free to do other things because there's a DMA engine that does the copy. And at the very end, when when the transfer is done, there's an interrupt that gets triggered, and we can then handle the interrupt, and we know that our data is done, and then we can proceed and actually read the data into RAM from RAM. Bypassing page cache. I'm still confused. No, because into page cache pages. I get that the virtual address mapping to a physical address is done through a page table, and virtual addresses are organized in chunks of pages, right? But how do we determine, is this like determined like at when the computer starts up, like where do you know sort of like what the page table will look like? I'm very confused on how like the page tables are organized, like how the pages are organized. Like, let's say we say a page is 5096 kilobytes, which is a standard size, right? Then how we just know, oh, this is the page, and we'll just like we just know that it's organized this way. I said 4,000. 4 kilobytes. When I progress a virtual memory. So back to like how files, when we read from secondary memory and we're trying to copy, do we first request like physical address, or similarly we request like virtual addressing, and then there's a page table? Or like you were describing, there's some other mechanism, right? I'm like a little confused. this correct? What does it mean? The copy on the device cannot occur while another operation is being executed? I see what you mean. You're saying like the bottleneck is the copy because the device needs to have a DMA. Okay. Let's just chat explain this. It's blocking on the GPU side because the GPU, if it's already executing computation and it's trying to read or copy data into VRAM, it's only possible if you have a DMA that's free and there's some region in memory. I'm also trying to understand because I suppose it's very similar to how like when you read or write to disk is the same idea, right? Like does the OS like reserve a section of memory at runtime when you make the system call, or like there's just like a permanent pool of memory that exists for this? So I didn't know what a page cache was. how does the CPU tells it where to write into? And oh. If we don't pin it, the synchronization. So here what we're doing is we're initializing the stream pin memory, so this will always exist in RAM, this will not, and this is some tensor that exists on a CUDA device, and we are moving it to GPU and then doing some matrix multiplication. Okay, so this is important, right? So it has a DM engine that can do this, and the data is pinned onto memory, and we are doing this in a separate stream. The reason it must be in pin memory is that if it's in secondary memory, alright, let's see the explanation, but I have an explanation for each of these. The DMA is so that the GPU, if there's no DMA, then the GPU has to spend the time to do this. There's no parallelization that can happen. But interesting. For GPU, into some we're not allowed to directly read from memory, right? When we're copying, like same reason when you read data into disk, you can't just directly copy the data into, like the DMA engine of the hard drive can't just directly read whatever the data is at that memory address. You're first not allowed to. It first needs to get copied into some buffer that the DMA has access to, and then you can copy it. And this is for safety reasons. At any time, like, these pages could be swapped out. What should I write? DMA is that the right point? Like when we transfer data between the CPU from RAM onto secondary memory, or even like CPU onto secondary memory, like when you do x equals 5 and then you store 5 into some file, what actually happens? Is it the DMA of the CPU, like the on the computer that talks to I don't think that's how it happens, right? It's like the DMA of the secondary disk that reads from memory of your like your main memory, but before you do that, it has to be in like some kernel buffer, because you're not allowed to directly read from main memory. At least the hard disk is not allowed to. I don't know what's correct. Like if it's not pinned, the issue is that, like, I'm trying to understand why we're doing all of this, right? Is it mainly for security issues and also reliability issues, right? Because if it's a page, it can at any time be swapped out of main memory into secondary memory when we're referring to a variable. So if we're just directly referring to some like physical address, like it might get swapped out. Is that sort of the concern? But if it's in the buffer, in the kernel buffer, we are guaranteed that this data is there, and it's not gonna get swapped out or used for other things. Is that correct? Oh my god, this is a big rabbit hole. Wow, this is deep. I'm not sure if I can. I'm trying to internalize this. Interesting. And CUDA stream is just like a context of execution, right? Yeah, I've played around with CUDA streams, so each stream is sort of an abstraction to tell you that they can run independently, right? I don't know how to read this. Like, it's just telling these operations how long they take, right? Like, it's too small though. Host and device. it's a lot. Hmm. Okay, I am zoning out, I think. Okay.